Now here's an example of something I don't get to see very often. This is crossover or notch distortion. And I'm going to point at it right there. That's right there. That's basically an area without any bias. That means that one transistor turns on here and it shuts off, but it takes a little bit before the other transistor turns on here. This is the negative cycle, which would be handled by the PNP transistor. This is top would be handled by the NPN transistor. And you got this lag right here, and that causes the infamous notch or crossover distortion. And this is a complementary-symmetry little circuit I built on a breadboard. And basically it uses like an NPN and a PNP transistor. And as I just kind of explained, one transistor conducts for one half of the cycle and the other for the other half of the cycle. So they're opposite in polarity, meaning that, for example, the NPN transistor is going to conduct during the positive half, and then the PNP is going to conduct during the negative half. And because of this lack of bias in this basically area, basically this is like a dead zone. So that's why we get this crossover distortion, which is more noticeable at low volumes, and that's more noticeable at low volumes because this has nothing to do with your amplitude. That's why it's more noticeable. In fact, the higher you turn it up, the probably the less you'd hear it, because this always stays the same. So let me go ahead and see if I can't go ahead and turn up the signal amplitude right here, and maybe that can be seen when it goes. Now I'm turning it up here, and you just got to keep a watch here. It's should go into clipping sometime. Right there it is. You can see right there. And if you look at the notch right there, it really didn't get any bigger. Right there. So although it did start clipping, of course you would hear that clipping, right? But this has nothing to do with having a high amplitude. Anyways, I just wanted to point that out. Thanks for watching. I hope I kind of made sense.